Welcome back. Well, for some reason the end of my last video got, I didn't put it in, I forgot to put it in or something, so I'm going to have to do another one for the compensator part. So we finished off with the transfer function of this guy, which is the angular position to the input voltage is K over S, 1 plus ST M, 1 plus STL, that's the inductive time constant, and that's the motor one. Assuming we can factorize it, it probably will be like that. And the integrators, because we're going from velocity to position. Mechanical integrator I explained. So it's got a slope of minus 20 dB per decade, minus 40, passing through unity gain somewhere here. And then finally minus 60. And so that would give us a phase shift starting at minus 90 going down to minus 270, and not much phase margin if we had any. It depends on where we're operating here. If it was a lower bandwidth we might have a little bit of phase margin, but we, generally speaking, for if you wanted any kind of speed of response, which means making the bandwidth here as high as we can, unity gain crossover, then we would pay for that by having instability. So it seems you can't have both at the moment anyway. So what do we do? Well, the first thing we do is, it's probably just good practice, is we've only got one integrator here. It's probably a good idea to have two integrators at low frequencies, and that gives us quite a high gain at low frequencies, and that gives us more disturbance rejection, better tracking ability, and so on. And the motor will feel tighter when you actually try and move it as well. So in order to do that, we use this kind of PI compensator. This is the sort of one you see in PID, is a K proportional plus Ki upon S. But if we factorize it, we can write it as KPS plus Ki over S, or Ki into 1 plus something times S over S. We can call that something T, another time constant. So we end up with Ki times 1 plus ST over S. So Ki is some kind of gain, and T is our time constant. So that's the first compensator we're going to do. And what we're going to do is select that T to be Tm. If we do that, we will knock out the motor time constant. Explain that in a minute. But anyway, its bode-plot on its own, just for the PI compensator, is just a slope of minus 20 dB per decade. Then it goes flat again. So it's like as if we can put an integrator in a limited range of frequencies here and sort of take it out again. So we can put it in at low frequencies, take it out. Integrators aren't so good anywhere else other than at low frequencies, really. That's where you want to put them. You can't put them anywhere else because they just, the phase shift will ruin your system. So you want to put it at low frequencies. But which range of frequencies? Well, let's put it at the at here, at this point here, so that it just basically knocks that out, and we go minus 40 all the way. So that's something like this, minus 40 dB per decade through unity gain, and then the inductive time constant. So that goes minus 40 minus 60. But if we were to plot the phase of this, it'd be even worse than before, because this is minus 180 degrees phase shift, and so we've just created an oscillator. So on its own, a PI isn't really much good in this case, because it's just going to create pure oscillations. So we use this phase lead or phase advance compensator, 1 plus ST1 over 1 plus ST2, where T1 is greater than T2. And it looks like this. It's got a bode-plot, goes up at 20 dB per decade and flat. And we define T1 over T2 as the span ratio. That's also the ratio of this frequency to that frequency. I normally make that about 10 to 1. So sort of omega high over omega low, I normally call it. This guy's omega high, that's omega low. And if we plot the phase, it goes up to a nice symmetrical maximum and comes down. And the maximum phase occurs at the geometric root of omega high and omega low, square root of omega high, omega low. And that gives us about 55 degrees of phase margin. So we can put this in here somewhere. We could kind of put it in there, or we could put it anywhere really, depending on what bandwidth we're looking for. kind of looks convenient. We might just even need one 0, but you can't really put 1 0 in on its own. You kind of need the pole with the 0 because it's physically unrealizable to have a 0 on its own. So we'll put it in somewhere here, and we'll leave this pole just to, you know, attenuate the high frequencies. So putting in the phase advance, we now get a bode plot that's minus 40 dB per decade, and the phase lead or phase advance now gives us a rise of plus 20 dB per decade, and that takes the slope to minus 20. Minus 40 plus 20 is minus 20, so it goes down through unity gain. And this is a good sign when it goes through unity gain. It's minus 20 dB per decade. It's not a good sign if it goes through minus 40 or minus 60. And then the roll off at high frequencies, that's okay. There's a little bit of attenuation here. And provided the bandwidth here is satisfactory, we can get away with that. The ratio between this guy and that guy, oh sorry, this one and this one, is again this we call the span ratio. It spans unity gain, and this is our bandwidth, and that defines the speed of response, how fast the thing's going to, the rise time in other words. There's a lot of books that describe these things in the time domain, but it doesn't really help you much because it only kind of works for second order systems, and this works for any order system, bode-plots. So I want to make this as high as possible. For the moment we'll just put it there arbitrary, and this ratio is the span ratio, which we'll make 10 to 1. You can make it 15 to 1 if you wanted to. And that should give us 55 degrees of phase margin. And sure enough, the phase starts at minus 180 here because of the double integrator, but then the phase margin, the phase advance takes effect, and up it goes, back down again, and then after here it's pretty rubbish, but we're not too worried about that. But that's this pole pulls it down. But as long as we've got one unity gain crossover here, and we get this phase which is much greater than minus 180, so it'll be minus 140 or something like that at this point, then we'd be happy. And the overall transfer function would look like this. And this is in fact what I've got in the video, something like this. K over S squared, 1 plus ST1 over 1 plus ST2, and the inductive roll off. Now, just as a sort of added bonus, I wanted to say that this isn't quite the end of the story with motors, because they do have resonances in them as well. And if you have a resonant frequency, you want to put that up at high frequency. You want that out of the way of the unity gain point. So in other words, whatever the resonant frequency is, you have to operate much lower than that, at least 10 times. So if this is a resonance frequency here, for example, then this bandwidth needs to be at least 10 times lower than that, because this has got some ferocious phase shift associated with it, which will ruin any phase margins. If I try to move this up here, this isn't going to move, this resonance. It's determined by the mechanics of the system, the springness of the of the stiffness of the materials and so on. So that's not going to shift. It's just going to be rock solid, and the chances are there'll be other ones next to it as well. So you can't really sort of counteract it. You just have to sort of live with it and move your bandwidth down, to cope with it, or design using different materials. Notice if you made a mistake and this was too high, what will happen is that this goes up above or through 0 dB, and you end up with another couple of zero crossings. And if you've got zero crossings, you've got phase margins. So although we've got a phase margin here, we would have two other, well, these would be very close to one another. It'd almost be like one phase margin, but we've got a couple more phase margins. We could end up with 3 phase margins. That one would be stable. This one would be unstable. So what happens is you get a stable response, and the oscillations due to this guy is at that frequency as well, is superimposed on top of the response. This is called a parasitic oscillation. Slightly different in op-amps, parasitics, same kind of idea, but of course in op-amps it's maybe slightly different reasons and so on. But you end up with if you get a nice response like this, what you'll get is your structural resonance superimposed on top of that, which is no good, obviously. So you need to keep this guy down below 0 dB, maybe 6 dB down or something like that from crossing over. And this is another restriction that if you wanted to actually add more phase advance, a second phase advance, and this is possible, but you've got to be careful because phase advance has got a high frequency gain, as we've just seen, and what that will do is move this up. So if you've got resonances and you put in more than one phase advance, you might find that you, instead of stabilizing it more, you actually end up destabilizing it at the high frequencies, even though it's stable at the unity gain point. So it is possible to go through unity gain asymptotically flat. If you added a second phase advance, that would give you a lovely, amazing amount of phase margin, and you might just be able to manage to squeeze it through, because although asymptotically it doesn't make much sense, the actual plot will cross over and hopefully cross over just once, and it should work. So it's not perhaps unusual to have more than one phase advance if you can get away with it. Just like you can have more than one integrator, why not have more than one phase advance? But if we keep the bode plot looking something like that, and with a steep response slope at low frequencies, going through about -20 or even flat, certainly not at plus. Once you start going through with a positive slope, you will end up with multiple crossings of the 0 dB, and you have multiple phase margins, and that can lead to interesting effects as well. Anyway, so yes, you want to do that, and then roll off at high frequencies to attenuate any resonances or noise there. If you did go through in a positive slope, some people want to know this, what would happen is it would go down like this, and then it would go up like that, and it would go down like that. It would be something like that. So you'd end up with 1, 2, 3 phase margins. And it's possible all 3 phase margins could be stable, but that doesn't really help you, because they've kind of got different speeds of responses. And what I've found, and you don't see this in any textbook, is that you get responses like this. It sort of goes up, and then it goes in reverse, and then it goes up again. It does things, strange effects like that, which you don't really want. So although it's interesting to do that, you want to keep the slope -20 dB per decade nominally, or flat if you want 2 phase advances. Okay, so that's about it. Thanks. Bye bye.